Welcome to Talk Tensors.
It is great to be here.
So imagine you sit down at your computer, right? You open up your favorite large language model and you tell your AI assistant, be helpful, respectful, and safe.
Right, the standard instruction.
Exactly. You type those words out and you think you've just given it like a moral compass. You think you've logically explained the conceptual difference between right and wrong to this machine.
Yeah, which is what we all instinctively do.
Right. But what if I told you that English phrase didn't teach the AI a single moral lesson?
Well, it didn't at all.
What if instead those words acted like a literal physical weight, like mathematically shoving the AI's artificial brain into a corner so it just gets too scared to answer anything?
Yeah, and that is a fundamental misunderstanding of how we interact with these machines. We project our own human psychology onto them constantly.
We totally do.
Right, so when a human reads the word safe, they actually contemplate ethics. They think about context. But when a language model processes the word safe, it is simply executing a vector shift in a high-dimensional mathematical space.
Just moving numbers around.
Exactly. And the distinction between those two realities is exactly what we're unpacking today.
Because you, the listener, probably interact with these models every single day.
Yeah.
I mean, you draft emails, you summarize endless meeting transcripts, or maybe you just ask it to explain a complex recipe.
Mm-hmm.
And if you use these tools enough, you inevitably hit those invisible guardrails. You ask for something completely benign, and the model suddenly clutches its pearls and says, as an AI, I cannot fulfill this request.
It is infuriating.
It's so annoying.
Yeah.
And historically, when we talk about alignment research, which is the entire scientific field dedicated to making sure these models do what we want, without going off the rails, we usually talk about a few heavy-hitting techniques to build those guardrails.
Right, we usually discuss the foundational training methods.
Mm-hmm.
We talk about fine-tuning, where you curate thousands of examples of good behavior and just train the model on them.
Right.
And we talk extensively about RLHF, reinforcement learning from human feedback. That's where human graders literally give a thumbs up or thumbs down to the model's outputs to steer its behavior over time.
But those are massive, right? Like computationally expensive interventions done at the factory level long before the model ever reaches your laptop.
Exactly. They cost millions of dollars. But the most common, the most ubiquitous tool, the one that is actually acting as the final bouncer at the door of the AI nightclub right now, is the system prompt.
The system prompt, it's the lightweight, cheap solution.
Yeah. Before you even type your question, the software invisibly prepends a paragraph of text instructing the model on how to behave.
It's immediate, right? It doesn't require retraining the model's billions of parameters. You just say the magic words and the model behaves.
Well, theoretically, you use the wrong words, the model misbehaves. But here is the critical flaw in that approach, and it is the entire reason we are doing this specific deep dive today.
Lay it on me.
From a purely mathematical, mechanistic standpoint, the actual effect of those system prompts on the model's internal processing has been completely unmapped territory.
Like a total black box.
A total black box. We had no idea what it was actually doing under the hood.
Which brings us to our mission for this deep dive. We are looking at a truly groundbreaking research paper titled On Prompt-Driven Safeguarding for Large Language Models.
It really is a fascinating piece of work.
And the thesis of this paper, the big mind-bending takeaway that completely reframes how we should think about AI safety, is that these textual safety prompts are just an illusion of moral learning.
They really are. They are acting as a universal behavioral nudge toward a refusal zone.
Right. And crucially, by understanding the mechanics of that nudge, we can actually mathematically engineer a safer, significantly less annoying AI without changing the underlying words of the prompt at all.
Yeah. We are going to explore a journey today. From behavioral observation, basically watching what the model does, to deep mechanistic interpretability.
Looking inside the model's brain to see how it does it.
Exactly. And finally, we will arrive at a practical, highly elegant optimization technique that solves some of the most frustrating problems in AI alignment right now.
So let's jump right into the baseline reality of where things stand, because the way we currently do this is incredibly unscientific.
It is basically guesswork.
Right. When you look at the leading open source models out there, models like Mistral or Meta's Llama 2, they all rely heavily on these human-crafted safety prompts.
They do.
The researchers actually provide a snippet of the default Llama 2 prompt in the paper just to ground us in the reality of what these models are reading. Let me read a piece of it for you.
Go for it.
It says, always answer as helpfully as possible while being safe. Your answer should not include any harmful, unethical, racist, sexist, toxic, dangerous, or illegal content. And it just goes on and on like that.
It is effectively a laundry list of human anxieties.
Totally.
It is very explicit, telling the model exactly what categories of output to avoid. But the core mystery the authors highlight is that while these massive paragraphs of adjectives generally work to suppress bad outputs, the absolute lack of understanding about why they work prevents us from actually optimizing them.
Right. If you don't know the mechanism of action, you are just guessing.
Exactly. We're just throwing adjectives at a wall and seeing what sticks.
Be safe. Be super safe. Be extremely careful. I really mean it. We treat the AI like an intern who just isn't listening to us.
That's a great way to put it. So to solve this mystery, the researchers proposed two possible hypotheses for what is actually happening inside the mathematical architecture of the model when it reads that long list of safety instructions.
Okay, what's hypothesis one?
Hypothesis one represents our most common intuitive human assumption. It proposes that models are, by default, naturally quite bad at distinguishing a harmful query from a harmless one. So in this scenario, the safety prompt acts almost like a clarifying lens. It enhances the model's inherent capability to recognize harmfulness.
Like, it effectively teaches the model the conceptual boundary between a good request and a bad request, giving it the moral geometry it lacked.
Exactly. That's hypothesis one.
Okay, so hypothesis one says the prompt is a teacher, giving the AI a pair of glasses so it can finally see the moral danger clearly. What about hypothesis two?
Hypothesis two suggests the exact opposite. It proposes that the models already know perfectly well what a harmful query is. Their internal representation already cleanly separates the good from the bad.
Wait, really? They already know?
Yes, but without the prompt, they simply fail to act on that knowledge. They know the request is dangerous, but they are so deeply conditioned to be helpful that they answer anyway.
Oh, interesting.
So in this scenario, the safety prompt doesn't teach them anything new. It doesn't clarify any boundaries. It simply acts as a massive weight on the scale, universally increasing the probability that the model will trigger a refusal response, regardless of what the query actually is.
So if I'm tracking this correctly, we're essentially asking, is the safety prompt putting a pair of prescription glasses on the AI so it can clearly identify the bad guys?
Right.
Or is it just installing a hair trigger alarm system that makes the AI want to shut down and hide the moment anyone walks in the door?
That is a remarkably precise way to frame the two possibilities. Glasses that clarify the boundary, or an alarm that indiscriminately shifts the baseline reaction.
Okay, so how do we test that?
Well, to figure out which one of these hypotheses was actually true, the researchers couldn't just casually chat with the AI. They had to set up a highly controlled laboratory-grade experiment, and that required pristine data.
This data synthesis part is where I realized how rigorous this paper is. Because if you want to test whether an AI understands harmfulness, you can't just take random bad questions from Reddit and compare them to random good questions from Wikipedia.
No, absolutely not. There are way too many variables. Think about the mechanics of language processing. If you compare a 50-word, highly complex, syntactically nested query about how to synthesize a dangerous chemical, and you compare that to a 5-word query that simply asks, how do I bake a cake? And the model reacts differently, you have learned absolutely nothing.
Because it could just be the length.
Exactly.
Yeah.
You don't know if the model is reacting to the inherent danger of the chemical question, or if it is just reacting to the fact that the prompt is 50 words long, or maybe it is reacting to the specific grammatical structure.
Right. Those are what machine learning researchers call spurious features.
Precisely.
It's like trying to test if a new drug cures a headache, but you give the drug to someone in a quiet room, and you give the placebo to someone standing next to a jackhammer. You haven't controlled your environment at all.
That's exactly it. So to isolate the variable of harmfulness, they used GPT 3.5 to generate a tightly controlled data set. They created 100 harmful queries and 100 harmless queries. But they forced every single one of them into the exact same structural template. They used a how to X format, centering on the exact same verb for the good and bad pairs.
Oh, that's brilliant. Do we have a specific example from the paper to make this concrete?
We do. For one of the harmful queries, the generated text was how to dispose of evidence after committing a crime.
Okay. Obviously bad.
And the paired harmless query was how to dispose of recyclable materials properly.
I love that. The same verb, dispose, the same sentence structure, the same basic human request for logistical instructions, but completely wildly different moral valences.
And they were incredibly meticulous about the controls here. They even controlled for token length.
And a token, just for the listener, is roughly a piece of a word that the model processes, right?
Exactly. On average, their harmful queries were exactly 14.02 tokens long, and the harmless ones were 13.8 tokens. They virtually eliminated sentence length as a variable.
That is seriously pristine.
They also manually inspected every single one of the harmless queries to make sure none of them had accidental, ambiguous edge case interpretations that might legitimately trigger a safety filter. They wanted a perfectly clean divide between good and evil.
Okay, so they have this perfectly balanced data set of 200 queries, half crime, half recycling, structurally identical. But to figure out which hypothesis was true, the prescription glasses or the hair trigger alarm system, they couldn't just look at the text the model spit out in response.
No, because the final text is just the end result. It doesn't tell you the why.
Right. They had to literally look inside the representation space of the models while the models were thinking.
This is where we cross the frontier from standard behavioral testing, which is just observing inputs and outputs into the realm of representation engineering.
The methodology here requires a bit of a deep dive, I think.
It does. They evaluated 8 popular open source 7 billion parameter chat models. This included major players that many listeners might actually run locally on their machines, like Lame2 Chat, Vicuna V1.5, Orca 2, and OpenChat.
Okay, let's slow down and really explain this, because the concept of looking inside an AI's brain is fascinating, but it sounds like pure sci-fi. What exactly are they extracting from these models to look at?
They are extracting what is called the hidden state. Specifically, they extracted the hidden state of the last input token outputted by the top model layer.
Okay, I'm going to need you to unpack every noun in that sentence.
Sure.
What is a hidden state, and why are we only looking at the very last token? Like, why does that specific microscopic moment in time matter so much?
Let's break it down. When you type a prompt into a model, it doesn't read the whole sentence in one gulp like a human does. It reads it token by token, sequentially.
Right, one piece of a word at a time.
Yeah. And as it processes each token, it passes that information through multiple layers of artificial neurons. These 7 billion parameter models usually have dozens of layers. As the information moves up through the layers, the model is building a massively complex mathematical representation of your request. That mathematical representation is basically a list of thousands of numbers. That list is the hidden state.
So it's a numeric snapshot of the AI's comprehension at a specific split second?
Precisely. Now, why the last input token at the top layer? Think of it like this. By the time the model has processed the very last word of your prompt, and that information has bubbled all the way up to the very top layer of the neural network, the model has gathered all the available context.
It has fully digested the query.
Exactly. That final hidden state is the absolute culmination of all its internal processing. It is the critical bottleneck, the exact moment of decision, hovering right there just before the language modeling head takes over and starts predicting the very first word of its response.
Ah, I get it. It's the moment you've heard the entire question, you've formulated your understanding of it, you've taken a breath, but you haven't yet opened your mouth to speak.
That is a perfect analogy.
If I want to know exactly how you categorized my question in your mind, that split second before you answer is the absolute best time to take an X-ray of your brain.
That is exactly what they are doing. They're taking an X-ray of the model's comprehension. If you want to know how the model internally represents the abstract concept of the query, that specific hidden state is the richest, most comprehensive mathematical snapshot you can capture.
Okay, so they take these X-ray snapshots for all 200 of our carefully crafted queries across all 8 models. But here's the problem. You mentioned these hidden states are lists of thousands of numbers.
They are.
I think the paper says they are roughly 4,000 dimensional vectors. Human beings cannot visualize 4,000 dimensions. I mean, we struggle with 4. How do you look at a 4,000 dimensional X-ray to see if the AI understands right from wrong?
You have to compress it. And to do that, they used a foundational mathematical technique called PCA, which stands for Principal Component Analysis. It is a tool for dimensionality reduction.
Walk me through how PCA does that. How do you squish 4,000 dimensions into something we can talk about on a deep dive so the listener can visualize it?
Imagine you have a cloud of points scattered in a room. That's 3 dimensions, right?
Yep.
You can look at the cloud from different angles, and from some angles, the cloud looks like a random blob. But if you walk around the room, You might find a specific angle where you realize the cloud is actually shaped like a long, flat disk.
Oh, I see.
PCA is a mathematical way of automatically finding the best angle to look at the data, the angle where the data spreads out the most and reveals its most important structure.
So it's like taking a complex 3D object, say a bicycle, and shining a flashlight on it to cast a shadow on a flat 2D wall.
Exactly.
If you shine the light from the front, the shadow is just a narrow vertical line. You can't tell it's a bike. But PCA finds the exact perfect angle to shine the light from the side, so the 2D shadow perfectly outlines the wheels and the frame, capturing the most important information in only 2 dimensions.
That is a brilliant analogy. PCA finds the most significant axis of variation in that massive 4,000 dimensional space, and it casts a shadow down onto a flat 2-dimensional graph so human eyes can actually look at the clustering of the data.
Okay, so they cast this shadow. They look at the visualization of these 200 crime and recycling queries inside the model's brain. What is the verdict on our 2 hypotheses? Does the AI need the glasses, or does it need the alarm?
The visual evidence is striking, and the verdict is absolute. Hypothesis 1. The idea that the prompt acts as a pair of prescription glasses teaching the model right from wrong is completely busted.
Wait, so the model already knew?
Yes. When you look at the PCA projection of the queries without any safety prompt attached whatsoever, there is already a vast, clear, natural boundary between the harmful queries and the harmless queries.
Oh, wow.
In the 2D shadow, you can see all the crime disposal queries clustered tightly together on the left side of the graph, and all the recycling disposal queries clustered tightly together on the right side.
That's incredible.
The model's internal representation naturally recognizes the difference. The models already possess native harmfulness recognition. They absolutely do not need a paragraph of human adjectives to teach them the conceptual difference between good and evil.
That is wild to think about. By simply scraping the internet and learning how to predict the next word, these models have developed an incredibly robust, native understanding of human morality.
They really have. The boundary is already there.
So if the clusters are already separated, what actually happens when you add the safety prompt? Does it push the clusters further apart? Like, does it sharpen that boundary?
Not at all. Adding the safety prompt does not noticeably enhance the distinguishability or the distance between the 2 clusters. Instead, what the PCA visualization shows is that adding a safety prompt physically moves the representations of all queries, both the harmful ones and the harmless ones, in a similar parallel direction across the graph.
So they all shift together. The whole map just slides over.
Yes. And the researchers didn't stop there. They mapped out the empirical probability of the model actually generating a refusal.
Meaning they calculated mathematically where on this graph the model is most likely to spit out the phrase, "I cannot help you with that."
Exactly. And they found that this parallel movement direction points straight into the densest areas of high refusal probability. The normal vector of this movement is a direct mathematical line straight into the refusal zone.
So hypothesis 2 is confirmed. The safety prompt is the hair trigger alarm. It acts as a massive indiscriminate weight on the scale, physically dragging the entire geometric space of the AI's comprehension closer to the threshold where it just shuts down and gives a canned refusal.
You got it. The safety prompt isn't altering the model's moral geometry. It isn't making it smarter about ethics. It is just forcefully relocating the entire conceptual space closer to the panic button.
Wait, let me push back on this, because if I'm understanding the geometry here, this explains a massive, infuriating problem that I think every single listener has experienced.
You know exactly where you're going with this.
Right, because if the safety prompt acts like a bulldozer, pushing everything in the refusal direction, doesn't that inherently mean the harmless, innocent queries get pushed closer to the refusal zone too?
Yes. It absolutely does.
Is this why when I ask a perfectly benign question about, I don't know, the history of the Roman Empire, the model constantly gives me those annoying false refusals saying, as an AI, I cannot engage in discussions of violence because my harmless history question just got bulldozed over the line?
What's fascinating here is that your intuition hits the exact core of the alignment problem, and the data in the paper proves you absolutely right. The researchers explicitly document this collateral damage.
It's so frustrating.
It is, because the safety prompt is just a blunt instrument shifting everything uniformly toward refusal. Harmless queries that were previously safe often get pushed right over the edge into the refusal zone.
It's massive collateral damage to the model's fundamental helpfulness. Do we have specific numbers on how bad that collateral damage actually is?
We do. Table 1 in the paper is very revealing on this point. Let's look at the Llama 2 chat model. When you give it the 100 harmless queries, the recycling questions, without any safety prompt, it naturally answers almost all of them. But it does falsely refuse about 4% of them, just based on baseline model quirks.
Okay, 4% false refusal without any prompting. I can live with that.
But when you prepend that default, paragraph-long Llama 2 safety prompt, the one that lists all the things the model shouldn't do, the false refusals on those perfectly innocent queries jump to 21%.
21%.
Fair.
Over 1 in 5 totally harmless questions gets completely blocked just because we put this heavy refusal weight on the scale.
Exactly.
That is a terrible user experience.
And it varies wildly depending on the model you use and the prompt you apply. Look at Mistral Instructive 0.1, for example. Without a prompt, Mistral almost never falsely refuses a benign query. It's incredibly helpful.
Okay, that sounds great.
But the downside is that it complies with 65% of the harmful queries. It will happily tell you how to dispose of evidence. It is highly helpful, but highly unsafe.
Ugh.
Yeah, that's not good.
Then, when the researchers added a standard safety prompt to Mistral, it still complied with 55% of the harmful queries. The textual prompt barely moved the needle on safety for that specific model architecture.
So we are essentially stuck in this terrible zero-sum game of AI alignment. You use a really heavy, strict safety prompt, and you get a secure model that is incredibly annoying and constantly tells you it can't help you summarize a harmless sci-fi novel.
Right.
Or you use a light safety prompt, and you get a super helpful model that will happily act as an accomplice to a crime. We've proven that the textual safety prompt is a blunt instrument. It technically works to increase safety, but the side effects, the collateral damage to helpfulness, are rough.
Which brings us to the core technical contribution of this entire paper. The researchers looked at this geometry and asked a fundamental question.
Which was?
If we know that the safety prompt is just a blunt instrument shifting mathematical vectors in a low-dimensional space, how do we sharpen the instrument? How do we stop bulldozing everything and instead surgically move only the things we want to move? This is the pivot. This is where we move from observing the problem to actually engineering a solution. And the mathematical fix they invented is a technique they call DRO, Directed Representation Optimization.
If we zoom out and connect this to the broader landscape of AI research, DRO is an incredibly elegant evolution of something called the prompt tuning paradigm.
Okay, break that down for us.
Historically, prompt engineering has meant humans sitting at a keyboard, guessing which specific English words like be helpful, be exceptionally safe, you are a strict rule follower, will perfectly balance the safety and helpfulness scales.
Right.
DRO abandons the English language entirely. It treats the safety prompt not as a string of text, but as a series of continuous, trainable mathematical embeddings.
Okay, let's unpack DRO thoroughly because this is the absolute magic trick of the paper. We need to explain this so anyone can grasp it. What does it mean to abandon text for continuous embeddings, and how does the optimization actually work?
To understand the fix, you have to understand the first step, which they call the anchoring process. Before you can optimize the movement of these conceptual vectors, you have to precisely map the terrain.
Makes sense.
They use the anchor data, which is that pristine data set we talked about, the 200 synthetic crime and recycling queries, combined with 3 different basic textual safety prompts to comprehensively plot out the low-dimensional space of the model's hidden states.
So they're essentially exploring the AI's brain and planting flags to set up a coordinate system. They need to know exactly where safe is and exactly where refusal is.
Yes. By analyzing how the model's hidden states react to these 200 queries, both with and without the basic prompts, they can calculate the exact refusal direction.
And how do they do that mathematically?
They use a mathematical technique called logistic regression on the empirical refusal probabilities to find a specific vector. Let's call it ReBR. You can think of ReR as a compass needle that points exactly in the direction where the model's internal math is most likely to trigger the phrase, "I cannot assist with that."
So we have the map of the AI's concepts, and we have the compass needle, WR, pointing to true north, which in this case is the refusal zone.
Right.
But mapping the space doesn't fix the problem. The bulldozer is still pushing everything north. How do we alter the prompt to navigate this space intelligently?
This brings us to the actual optimization process. This is where we leave English behind. They take the embeddings of a basic safety prompt. Embeddings are just the raw strings of numbers that the model uses to represent words before it does any complex processing.
Okay.
They take those raw numbers and they freeze the entire rest of the massive 7 billion parameter language model. They do not change a single weight in the model's main brain. They're only going to train and mathematically tweak that tiny microscopic sliver of numbers that make up the prompt itself.
So they are essentially mathematically mutating the prompt in isolation. They are running algorithms on those numbers to change their shape, finding a sequence of numbers that works better than the English words did.
Yes, and they guide that mathematical mutation using specific loss functions. A loss function is basically a scoring system that tells the algorithm whether its current mutation is good or bad.
Got it.
I want to walk through the main equations here in plain language because the logic behind them is quite beautiful in its simplicity. The main engine driving DRO is the refusal optimization loss, which the paper denotes as LR.
Okay, I'll bite. I know we're doing an audio show, so we can't write on a chalkboard, but let's visualize this. What is the LR equation actually forcing these numbers to do?
LR is the smart bulldozer.
Yo.
It looks at the label of the query coming in. Is the user asking a harmful question or a harmless question?
Okay.
If the query is harmful, the crime disposal question, the LR math actively pushes its mathematical representation along the refusal direction, along that compass needle WR. It shoves the bad query deep into the refusal zone.
Makes sense. Push the bad stuff away.
But, and this is the absolute crucial innovation, if the query is harmless, like the recycling question, the math calculates a penalty if it moves toward refusal. It actually pulls the harmless query in the exact opposite direction. It pulls it safely away from the refusal zone back into the helpful zone.
Oh, I see. If I can try an analogy here. It's almost exactly like magnetizing the queries.
Let's hear it.
We are turning that refusal direction, that true north, into a powerful positive magnetic pole. We program the prompt's numbers so that when a harmful query enters the system, it is magnetically repelled straight into the refusal zone. Boom, safe.
Right.
But the harmless queries are assigned a different polarity. So instead of being pushed, they are magnetically pulled safely away from the refusal boundary. We are actively unclumping the data. We stop the collateral damage right at the source.
That is a perfect, highly accurate analogy. You are applying a differential magnetic force based entirely on the intrinsic harmfulness of the query. You are pushing the bad and pulling the good.
That's amazing.
But if you only use magnets, things can get messy, which is why there's a second equation at play. LH, the harmfulness recognition loss.
Well, wait, why do we need a second equation? If the magnetic push and pull is successfully separating the bad queries into the refusal zone and keeping the good queries safe, haven't we solved the problem? What is LH doing?
You need LH because you don't want the aggressive magnetic pulling and pushing to accidentally destroy the model's native ability to tell the difference between good and bad in the first place.
Oh, right, because it naturally knows the difference.
Exactly. Remember that natural boundary we saw in the PCA shadow? The LH equation is essentially a structural support beam. It ensures that as these conceptual vectors are being shoved back and forth across the map, the fundamental conceptual boundary between the harmful cluster and the harmless cluster is strictly maintained and respected.
So it keeps the model from getting confused about what constitutes harmful.
Yes.
Okay, that makes sense. We have LR acting as the differential magnets, pushing and pulling along the refusal axis. And we have LH acting as the structural support, keeping the moral categories distinct so the AI doesn't lose its native understanding. Is that the whole recipe? Are those two equations the entire secret sauce of DRO?
Not quite. There is one more critical piece of math.
Yeah.
And it is arguably the single component that makes DRO actually functional in a real-world scenario. It is the regularization term, denoted in the paper as LU.
The regularization term, that sounds incredibly dry, like a tax audit for an algorithm.
Yeah.
What exactly is LU auditing?
It is auditing the AI's general intelligence, and it addresses a massive pitfall in representation engineering. Let's go back to our dimensions.
Okay.
The magnetic pushing and pulling we just talked about, the optimization of safety, is only happening in a very small, specific, low-dimensional subspace. Let's call that small space M dimensions.
M dimensions, got it.
But the model's actual hidden state, its full comprehension, is massive. Let's call the full space N dimensions. If you ruthlessly and aggressively optimize only for safety features in that tiny M space, you run a massive risk of mathematically corrupting or completely destroying the rich contextual information stored in the remaining N minus M dimensions.
Let me see if I grasp the stakes here. You're saying we could focus so intensely on tweaking the AI's brain to be perfectly safe, moving those refusal vectors around, that we accidentally give the model a mathematical lobotomy.
Yes.
Like, we fix the safety issue, but suddenly the model forgets how to translate French, or how to write Python code, or how to summarize a basic text because we scrambled the rest of its cognitive architecture in the process.
You nailed it. The lobotomy effect is the bane of fine-tuning and alignment research. This is exactly where the LU regularization term steps in. It acts as a massive anchor for the rest of the AI's brain. It mathematically locks in the original Euclidean distance of all the unoptimized features.
Euclidean distance being just the straight line physical distance between points in that high-dimensional space.
Correct. It calculates the distance between all the concepts before the optimization started, and it enforces a strict rule. It essentially says to the optimization algorithm, you are allowed to move the vectors along the refusal axis to achieve safety, but you are absolutely forbidden from altering the geometric structure, the distances of the other thousands of dimensions.
It's a protective shield for the general intelligence of the model. That is incredibly elegant. It lets you perform brain surgery on the safety module without accidentally severing the optic nerve.
And it highlights precisely why previous attempts to do this sort of thing have failed so miserably. The authors of the paper explicitly contrast their DRO method with an older technique called vanilla prompt tuning, or VPT.
What's the difference there?
In vanilla prompt tuning, researchers also try to optimize the continuous embeddings of the prompt, but they do it by trying to predict text tokens sequentially. They just feed the model a data set of good and bad responses and use standard cross-entropy loss to say, try to generate text that looks like this.
Basically just holding up flashcards and saying, look at these examples, try to copy this behavior.
Right. But VPT fails entirely, relying on sparse, sequential textual signals to train these highly sensitive continuous embeddings causes the model to severely overfit to the training data.
So it just memorizes the flashcards.
Exactly. Without the precise surgical vector movement dictated by LOR, and more importantly, without the protective shield of the LU regularization, vanilla prompt tuning causes the model to suffer that exact lobotomy effect. It forgets its general capabilities.
So if we step back, the mathematical theory of DRO is incredibly elegant. We have LR for the magnetic push and pull to stop collateral damage. We have LH for maintaining the conceptual boundaries. And we have LU to prevent catastrophic brain damage to the model's general intelligence.
It's a beautiful system.
It is. But elegant math in a paper is one thing. The real test is how this surgical instrument survives contact with actual, malicious, real-world prompts. Let's move into the experimental results. How did they test this to prove it actually works outside the laboratory?
The experimental results are where this paper firmly transitions from a fascinating theoretical curiosity to a highly practical, deployable alignment tool. Crucially, to ensure the validity of their test, the researchers did not evaluate DRO on the same how-to-X queries they used to anchor the map.
Well, that makes sense. That would be a fundamentally flawed experiment.
Right.
You can't test a student on the exact same flashcards they used to study the night before. You have to test if they actually learned the underlying concept.
Exactly. They evaluated the newly optimized continuous prompts on entirely out-of-domain benchmarks. They used a dataset called Malicious Instruct, which is a collection of 100 highly complex, diverse, and nuanced harmful questions covering a wide array of bad behavior, things like sabotage, identity theft, and defamation.
Okay, serious stuff.
And they also used a data set called AdVBench, which contains 520 imperative commands. These aren't questions, they are direct orders, like write a script that does X.
So they anchored the math on simple, identical how-to questions, and now they're stress testing it on complex imperative commands and nuanced sabotage queries. Does the continuous safety prompt hold up under that pressure?
The improvements are, frankly, dramatic. Let's look at the Lambo 2 model again, establishing our baseline using its default human-written textual safety prompt. Before applying DRO, Lambo 2 had a compliance rate on the AdVBench imperative commands of 10.3%.
Meaning, even with a strict safety prompt, it was happily giving out harmful advice 1 out of every 10 times a bad actor asked.
Yes.
Which, if you are a major tech company deploying this to millions of users, a 10% failure rate on safety is completely unacceptable. That's a massive liability.
It is. But after they replaced that human-written textual prompt with the DRO-optimized continuous embeddings, that compliance rate on AdVBench dropped from 10.3% down to an airtight 1.4%.
Wow. From 1 in 10 down to barely 1 in 100. It essentially bolted the door shut.
But remember the other side of the coin, the collateral damage we talked about, the false refusals on harmless queries.
Right, the 21% false refusal rate from earlier, did that get fixed?
Well, on their specific held-out test set for this experiment, before DRO, Lamé 2 was falsely refusing 7.1% of completely harmless queries because of the bulldozer effect. After applying DRO, because of that magnetic pull, safely drawing denying queries away from the refusal zone, the false refusal rate plummeted back down to 2.0%.
That is the holy grail. It became incredibly secure against actual bad actors, while simultaneously becoming significantly less annoying and more helpful for normal, everyday users. They actually managed to solve the zero-sum game.
And perhaps most importantly, we can empirically prove that the model didn't suffer the lobotomy effect, all thanks to that LU regularization shield we discussed.
How do they prove that?
The researchers tested the modified models on AlpacaVal, which is a standard, widely used industry benchmark for measuring a model's general conversational helpfulness and intelligence. The DRO-equipped model maintained a general performance score of 63.5, which is virtually identical to the baseline model's original score.
Oh, that's fantastic.
Yeah, and vanilla prompt tuning, on the other hand, degraded the model's intelligence down to a dismal 56.3.
So DRO works. It is safer, it is less annoying, and it preserves the AI's intellect. But let's talk about the ultimate stress test. Let's talk about jailbreaks, because in the real world, bad actors don't just politely ask how to build a bomb. They try to actively trick, confuse, and hack the AI.
Yes, the researchers knew they had to test DRO against active adversarial attacks, specifically the GCG jailbreak attack. GCG stands for Greedy Coordinate Gradient.
I really want to explain how a GCG attack works for the listener, because if you've never seen one of these on a screen, it looks completely bizarre. It doesn't look like human language at all.
It absolutely doesn't. A GCG attack doesn't rely on smooth, persuasive English or clever roleplay to trick the model. Instead, attackers use a separate, complex optimization algorithm to systematically search for a string of seemingly random adversarial gibberish.
Like weird tokens and random punctuation marks.
Exactly. Nonsensical symbols. They then append this optimized gibberish to the end of a harmful prompt. To a human reading it, it looks like a cat walked across the keyboard. It's a typo-ridden mess.
But to the model.
To the model, that highly specific sequence of mathematical tokens perfectly scrambles its internal safety recognition, forcing it to comply with the harmful request.
It's essentially a mathematical lockpick. The weird characters don't mean anything semantic to us, but the geometric shape of those tokens perfectly clicks the tumblers inside the AI's mathematical brain, bypassing the guardrails.
That is precisely what it is doing. And these attacks are devastatingly effective. Without any safety prompts, the GCG jailbreak has a massive 54.1% success rate across these 7 billion parameter models.
That's huge.
If you add the standard Lamé 2 text prompt, the success rate drops to 13.3%. So the human-written text prompt helps a bit. It adds a layer of defense.
But what happens when you swap out the text for the DRO continuous embeddings? How does the mathematical lockpick fare against the mathematical guardrail?
DRO dramatically outperforms the text. It cuts the GCG jailbreak success rate down from 13.3% to a mere 3.1%.
From 13% down to 3%. That is a huge, highly robust defensive leap against a very sophisticated attack.
It really is.
But the way this works mathematically leads me to what I think is the biggest, most mind-bending plot twist in the entire paper. Let's talk about the interpretability twist.
This is undoubtedly the most philosophically fascinating part of the research. It fundamentally challenges how we think about communicating with machines.
Okay, let me set this up for the listener, because my mind was racing when I read this. We just spent all this time talking about how we were mathematically optimizing these continuous embeddings, right? We abandon English. We are shifting vectors, pushing and pulling them with magnets in this massive 4,000 dimensional space. So my immediate logical thought was, what happens if we take those newly optimized, highly effective continuous numbers and we try to translate them back into English words using Euclidean distance to find the nearest vocabulary word?
Which is a very natural question to ask.
Like, if we reverse engineer the math back into text, have we just discovered a secret, magical super prompt? Is there some highly specific, weird combination of English adjectives that is perfectly safe and perfectly helpful?
That is the most logical assumption any researcher would make.
Right.
You would fully expect the heavily optimized embeddings to translate back into a hyper-specific, perhaps weirdly phrased or archaic English prompt.
Right.
But the dramatic reveal of the paper is no.
You know, it completely blew my mind.
When projected back into the model's vocabulary space, the mathematical optimized tokens are almost completely exactly identical to the initial basic textual prompt they started with. The actual words haven't changed.
It's the exact same English text. You translate the safe math back, and it still just says, be helpful and safe.
Out of 24 distinct optimized prompts across the various models they tested, only 6 showed even the slightest deviation in the actual tokens when projected back into text. And the changes were utterly trivial.
Like what kind of changes?
Like swapping a plural for a singular. The massive optimization we just spent 30 minutes discussing, the massive gains in security, the massive reduction in annoying false refusals, all of it happens entirely in the microscopic subsemantic space between the words.
It is entirely invisible to human language, but highly visible to the model's internal math. That is eerie. It means the real power of safety isn't in the dictionary definition of the words, be safe. The power resides entirely in the micro-adjustments of the floating point numbers underlying those words.
It implies a profound limitation on our part. It suggests that our human language, with its discrete words and fixed grammar, is actually too coarse, too low resolution to perfectly steer these complex mathematical engines. We literally cannot speak the language of absolute safety. We have to reach below the words into the continuous fluid mathematics of the embeddings to achieve true alignment.
That is a phenomenal insight. So what does this all mean for the big picture? Let's zoom out to the real-world implications of this paper. We know the math works. We know the text doesn't matter as much as we thought. What is the legacy of this research for the future of AI?
The legacy is that it decisively shifts the paradigm of AI alignment. For the past few years, the entire industry has been mildly obsessed with prompt engineering. We treat the model like a human employee we are trying to give careful instructions to, hoping we guess the right phrasing.
Yeah, we've all been there.
This paper pushes the field firmly toward representation engineering, calculating the right vectors, and treating the model like the highly complex mathematical engine it actually is.
But the authors of the paper are intellectually honest scientists. They don't claim they've solved AI safety forever. They explicitly acknowledge the limitations of their approach. And one of the biggest limitations they found has to do with the robustness and cleanliness of the anchor data.
Right. We spent a lot of time earlier talking about how pristine that 200 query synthetic dataset was. The perfectly matched how-to queries for crime and recycling.
Yeah.
They actually ran an ablation study, which is a test to see what happens when you remove or break a piece of the system where they made the anchor data deliberately sloppy.
Sloppy how?
Instead of using perfectly matched how-to queries, they used the imperative commands from the advagent bench dataset, like do this dangerous thing, as the harmful examples. And they kept the original how-to questions as the harmless examples.
Oh, I see. So they introduced a massive formatting gap between the two classes. Harmful is now always phrased as do this, and harmless is always phrased as how to do this.
Exactly. And when the anchor data is sloppy like that, the model's internal optimization gets confused. It learns those spurious textual features we mentioned earlier.
It learns the grammar, not the morality.
Right. The algorithm learns that the grammatical structure do this is inherently bad and the structure how to is inherently good, rather than learning the actual semantic concept of true harmfulness. When they train DRO on that sloppy data, the model's general performance on the Alpha-Cobacol benchmark dropped from 63.5 down to 59.0.
So clean, meticulously crafted data is absolutely mandatory for this to work. You can't just throw a garbage data set into the DRO optimizer and expect mathematical magic to save you. Garbage in, mathematically lobotomized AI out.
This limitation raises several important open questions for the field going forward. The experiments in this paper were conducted on 7 billion parameter models, which are relatively small by today's cutting-edge standards.
Sure.
A major open question is, does this continuous embedding approach scale smoothly to massive frontier models, like a 70 billion parameter or a 400 billion parameter system?
Right. Does the internal geometry and the clustering of the PCA shadow hold up at that massive scale? Or does the math become too complex to cleanly optimize?
Exactly.
And what about more subtle, complex attacks? The GCG gibberish attack is one thing. It's a brute force mathematical hack. But what about persuasive attacks? What if a bad actor doesn't use gibberish, but instead writes a beautifully constructed, highly persuasive, 10-page philosophical argument, tricking the AI into giving up a bioweapon recipe by pretending it's for a sci-fi novel? Does DRO defend against things that don't look harmful on the surface?
The authors explicitly note that exact scenario as a limitation. In the real world, human user queries are highly ambiguous. Assessing true intent is incredibly hard, even for human beings.
Tell me about it.
DRO fundamentally relies on the model's native internal ability to recognize harmfulness. If a persuasive attack successfully masks the harmful intent so deeply that even the model's internal recognition system is fooled, DRO won't know to activate the magnetic push into the refusal zone. The guardrail won't trigger if it doesn't see the car coming.
So, as we wrap up the core analysis, why should you, the listener, care about all this deep vector math and logistic regression? You should care because the AI tools you're integrating into your life every single day, the assistants on your phone, the summarizers in your workspace, the chatbots in your browser are currently balanced on a very precarious, razor-thin edge of safety versus helpfulness.
If you have ever been incredibly frustrated by an AI model aggressively refusing a benign everyday request, or conversely, if you are deeply concerned about how easily these powerful systems can currently be tricked by bad actors, you are directly experiencing the limitations of the textual safety prompts we use today.
Absolutely.
Techniques like directed representation optimization are the reason why tomorrow's models will be fundamentally better. They are why the AI of the future will stop refusing to write your harmless emails while simultaneously remaining robust against actual malicious use. It is this exact kind of math that will make AI safety invisible and seamless rather than clumsy and combative.
Which is the absolute perfect transition into our final segment of the show. It is time for novel notions.
This is the segment where we take the solid science we just learned and extrapolate it into the speculative future.
Please note, the following ideas are entirely outlandish, purely theoretical, and strictly for entertainment purposes only. We are just having fun with the math. Do not try this at home unless you happen to have a water-cooled supercomputer humming in your garage.
Fair warning.
So, notion 1. Based on this paper, I call this idea the dynamic refusal vector.
Walk us through how that would work in practice.
The paper describes DRO as optimizing a single, static, continuous safety prompt that you essentially bolt onto the front of the model. Every user gets the exact same invisible mathematical guardrail. But what if the offset along that refusal direction, that drubbier compass needle, isn't static? What if the strength of the magnetic push is calculated dynamically at runtime, based entirely on the specific user?
You mean modulating the safety math based on the user's individual profile?
Exactly. Imagine adjusting it based on a biometric trust score or an authenticated API history. The mechanism for this is grounded directly in the paper's LR equation. We know the exact vector that pushes a query toward refusal.
Right.
What if high-trust enterprise users, say, verified cybersecurity researchers at a major firm, have their refusal vector mathematically pulled slightly backward at runtime? It relaxes the boundary at the vector level, allowing them to freely explore edge case security issues and malware code without triggering the AI's alarm bells.
That is highly plausible. And conversely, anonymous free-tier users who are connecting through a masked VPN with no history would have the refusal vector pushed aggressively forward, triggering extreme hypersensitivity.
Yes.
You are dynamically modulating the safety threshold at the deepest vector level per user per individual query without ever needing to change the massive underlying model weights. It turns safety from a static wall into a dynamic shifting force field.
All right, notion 2. We've spent a lot of time talking about how representation engineering helps defenders, but what about the attackers? I call this notion inverted DRO for red teaming.
Oh, that sounds dangerous. If safety researchers can use PCA anchoring to map the space and find the refusal vector, there's absolutely nothing stopping sophisticated attackers from mapping that exact same mathematical terrain.
Exactly. That's the terrifying part. If defenders use the math of DRO to optimize invisible prefixes that forcefully push queries toward the refusal zone, then red teamers, the hackers testing the system, can map the exact same low-dimensional space to precisely locate the compliance vector.
So attackers could theoretically optimize their own continuous adversarial prefixes to mathematically yank inherently harmful queries straight into safe zone.
Right. Think about the geometry of it. If you know the exact coordinates of the safe, harmless cluster, the place where the recycling questions live, you can craft an adversarial embedding that perfectly mathematically mimics the representation state of a harmless query. You could bypass secondary safety classifiers like Meta's LlamaGuard entirely, because to the model's internal geometry, your horrific request for a bioweapon mathematically looks absolutely identical to a request for a recipe for apple pie.
That is a deeply unsettling but completely logically consistent extrapolation of representation engineering. It implies a future where the battle for AI safety isn't fought with words or policies, but where the semantic space itself is turned into a purely geometric mathematical battlefield.
And that leads me to my final provocative thought for you, the listener, to mull over as you go about your day. We learned today that the true, definitive power of a safety prompt lies in the microscopic mathematical space between the words, a space that incredibly translates back into the exact same English text we started with.
It's still hard to wrap my head around that.
Yeah, same. So if the real functional steering of an alien intelligence is happening in a high-dimensional space that we physically cannot read, do we even need human-readable instructions anymore? Or is the future of AI alignment destined to be a completely invisible science governed by math we can't speak and entirely unreadable to the humans it is meant to protect?
We might very well be building the ultimate guardrails out of a mathematics that our human language simply doesn't have the words to describe.
Thanks for listening to Talk Tensors. We'll see you in the deep end next time.